Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Okay folks, welcome to workshop 4 for Project Maths. Today we're going to have to look at a focus on patterns, okay? And today is going to pan out like this. We're going to have a small introduction to the emphasis of patterns in school, and it's quite a new thing, I suppose, from where we would have saw our algebra before from a school point of view. So that's the first part we're going to have a look at, and then we're going to introduce you to patterns, and there's 5 or 6 different problems there that we're going to have a look at in order to introduce you to the idea of patterns. That will take us right up to lunchtime. And then we look at algebra on the syllabus, because after we've looked at patterns, it should be more clear to you where this comes into play in terms of your algebra. That it's not a unit that you just go, right, that's my patterns covered, and now let me move on now and do my algebra, okay? It's a way of introducing your students to algebra and to keep that flow going throughout, okay? We'll look at some examples then from the exam papers and how it was examined using graphs. What information can you glean from just looking at a graph? Before it was very much do out your table, draw a graph, work with graph. Now there's a lot more of an emphasis as look, when you see a graph, what does that picture tell you? And you know yourself from newspapers and all kinds of research or anything like that, everything is displayed on a graph and they just assume that people are able to read them, okay? So we'll make a start then. It's a slightly different approach to algebra that we're having a look at today. Okay, so from primary school, we're all familiar with this from primary school, as in fill in the box. And really there, 3 6s are, and you're trying to get what goes in the box. Something plus 5 equals 12. Really at that stage, what's it a test of? It's really a test of their tables and their arithmetic, and it's not really a case of, well, I wonder, you know, what number goes in plus 5 to 12. It might be a case of what might the student be doing. They could be getting it by trial and error. Well, 6 and 5. Oh, well, that only gets me as far as 11. And then so forth and etc. It's not necessarily, they don't have an algorithm built up in how it goes. Then we get them into secondary school, into first year, and what do we start doing here? Okay, your rules start to come into play here in some way. Well, what do we have to do? We want to get rid of that 5, so we need to subtract 5 from both sides and so forth and etc. I want to get rid of my 3, so I divide both sides by 3. And even very early on in first year, what begins to happen? Yeah, let's forget the rules now. I know what happens. If it's added, I subtract. If it's multiplied, I divide, and so forth and etc. And all of a sudden, I'm brilliant at this. Next thing, third year. Are you all familiar with seeing this? Yeah. Okay, well, what has happened? They show a brilliant understanding in first year when you're teaching it, but next thing, when it's left behind, what happens then? What have they done in the first one? Very typical mistake. Not sure what rule to use, so mixing up which one to go with. Same again in the second one, very simple. You know, what happens when I bring across the equals? No rule there at all, but yet they're still obsessed with it. And in the last one then, 2x equals 6, the ultimate sin is what? Well, look, I'm not sure which, so I'll do both. Yeah. Okay? And that's your ultimate sin. And like, it's unfortunate something like that, because what about it? That transpires itself even right up to higher level leaving cert when they're working with algebraic fractions. Okay? They will bring a number over, divide it, and they will both change its sign and divide. Okay? So if they don't have their concrete basis from a very early stage, obviously then they're going to fall into traps. Okay? So what's happening? The procedure is taking over understanding. What has happened very quickly? In first year, they get the rules. What about it? If it's added, it's subtracted. If it's multiplied, it's divide. And then all of a sudden, they're the rules forever. And that means then they have no understanding of what they're doing. Okay? Now, so just a quote here. National and international mathematics assessments during the 80s and 90s reported that secondary school students, in order to cover their lack of understanding, resorted to memorizing rules and procedures, and that students eventually became to believe that this activity represented the essence of algebra. Now, what kind of led this along as well for us as teachers, do you reckon? this idea of let's learn off our algebra or let's learn off how we do it. What did they get at the end of their 3 years or the end of their 2 years? They got their exam. What about that exam? Very, very structured in terms of what? Your question 1 was a certain type of algebra. Your question 1 and 2 get to leave cert was a very particular type of algebra. So what was the idea? Well, if I practice enough of these, even though I may not know what I'm doing, it doesn't matter, I'll still be able to do what? Still be able to answer that question. Does that make sense? Because it's just, look, if I can churn out enough of practice of these, I will be able to do it, okay? And obviously then that causes a problem for students when they go on to a different level of mathematics, because why? There was no procedure there to start with, so they got over that fence, but then all of a sudden they're at another hurdle, okay? Now, some of the chief examiners' reports. So the Leaving Cert Ordinary Level 2006 said the following: common mistakes were combining terms leading to overall simplification and transposition errors, okay? So again, back to what we were talking about there, okay, in our first slide. Higher level, areas of weakness in candidates' answers, handling transpositions in algebraic type equations. So what have you moved on to there? Even at ordinary level, they're getting mixed up with numbers and so forth and etc. But at the higher level, what happens? They're moving on to their algebraic and manipulation of their letters, and they're still finding problems. Leaving cert foundation levels, there were transposition errors, and transposing accurately and with understanding is certainly a difficulty. Okay, so there's very little understanding there, it seems, for the foundation level student of how to approach this type of thing. And then Leaving Cert Ordinary Level 2005, average candidates experience difficulty with all but the most basic of algebraic manipulations and cope only with the most basic routines in solving equations. So basically, all the skills that we have drilled into them are gone. Does that make sense? As much as we've drilled into them at that stage, at Leaving Cert, it has left them, okay? Now, so how can we develop in our students a deeper understanding of what algebra is, okay? Instead of just routine procedure after procedure after procedure, okay? So what we're going to do is we're going to step back and see how it came about, okay? So the historical development of algebra. Okay, before 250 AD, ordinary language descriptions were used for solving problems, because if you think about it, I want to barter this for that and so forth and etc. There was no formal language around it. No symbols or special signs to represent unknowns, okay? It wasn't a thing. Everything was swap and barter, obviously. Now, after that then, Fontes introduced the use of letters for unknown quantities, but there were no procedures on how to use algebra. Fontes' maths was still presented as a story of how to do things. Now, all he was actually doing was, you know, when you're doing a maths problem, what do you realise? You start to use the same thing over and over again. So if you're using number of people per week, what do we tend to do? Call it N or call it W, because what happens? You just get sick of writing out the same thing over again. Same, that's all he was doing. Realising he was writing out the same thing over and over again, so that's where he was using his symbol for. Just to shorten things down, but it was still what? It was still very language based and not mathematical language, okay? Now, algebra was used then to get the result for an unknown. So whatever he called phi then, he then went off and said, well, look, I was trying to solve for this thing. It was the number of weeks, or it was the whatever the case may be, okay? But they were still not using algebra to express the general case, okay? There was no such thing as, so they were still at a problem of what? They could have done a problem like this today, to go back and do a problem very similar to it tomorrow, and what would they do? Start from scratch all over again. There was no procedure there. Does that make sense? Okay, they started from scratch all over again. Okay, now the late 16th century then, work began to be use a letter for a given as well as an unknown. So what now came into being? Now your equations started to make sense, okay, because they had their two unknowns. Letters were not just used now to shorten stories. They were starting to realise, well, look at the problem I looked at yesterday. Looks very like the one I'm looking at today. I wonder, is there some way we could look at these and formulate some way of doing all these type of problems, okay? So also in the late 16th century, it was now possible to use algebra as a tool for proving rules governing numerical relations. So it's very hard for us to imagine, but they had superb maths without any calculators or anything like that. But what about them? They had no way of knowing that it worked. They knew that 2 plus 5 gave 7, but they had no way of going, how do I know when I always add things, it always works, but at the same time they didn't have a rule for this. Does that make sense? So the rules then came upon us and they were able to go, wow, look, this is why it's all working, okay? Now, so what happened? What was the last thing that came about? procedures was the very, very last thing that happened. Okay, very, very last thing. So they were doing incredible maths, and what did they put on top of that? At the end of it then came the procedures. What do we do? Okay, so if the procedure were the latest development, are we doing the right thing in reducing to procedures so early? Okay, so let's see. In primary school, the equal sign is seen as an instruction. Okay, +5 equals what? Okay, so you have your 3 + 5 equals. Then they come into secondary school, and what does the equals mean to them at that stage? It means give me an answer. Ultimately, that's what it says to them. It does not really, even if they're taught it in primary school, the idea of equality doesn't really hold for them. Then if you tell them A + B equals, what will a good cohort of students write down for that one? Exactly, Joanne, A, B. Does that make sense? Because why? There's an instruction there with an equals, and what does that equal say to them? I need an answer. And that answer here is, well, I know it's not whatever, so I'm going to write down A, B. What could they write down? A + B, again, or B + A. But they're not comfortable doing that because they're not really familiar with what the equals is for, okay? And there you are in post-primary school and trying to get them used to what? What the idea of equality actually means, okay? So our old syllabus started with what? Expressions, procedures and equations. Now what have you noticed in the new syllabus? There's lots of question marks there because remember I'm going to look at the syllabus with you later on in the day. So what are we doing? We're leading up to what? Expressions, procedures and equations. Does that make sense? So instead of starting out with expressions, procedures and equations, we're giving them their own grounding first of all, and then we're going to move to expressions, procedures and equations. So there's a basis for where things come from, okay? So now, mathematics is the study of patterns, obviously, okay? Now look at all these hard words, okay? I left these behind me. At this stage, it's 20 years ago this year since I first set foot in Maynooth, and I was learning things like this. A pattern led you to a conjecture, to a proof, and then you went on to a formal procedure. What do we want our students to be able to do? Well, the same idea. They see a pattern, do you observe it? Okay, what's going on here? Can I generalise it and then, obviously then, bring it on to the formal? Now, they don't have to bring it on to the formal and an awful lot of stuff in secondary school because what are you trying to get them to do? That last step is very, very difficult, obviously. Does that make sense? They will in some of their formal proofs in geometry, but we're very happy if they're able to do what? See a pattern, can they observe what's happening in it, and then generalise from that. And what are they still following? They're still following the very strict mathematical procedure that would go on at a later level, okay? The next thing then, concrete to the abstract. Now this is something that I think we'd always be doing anyway. Words to abbreviations. Numbers, then go to variables, arithmetic properties of numbers, and then we go on to arithmetic properties of algebra. So algebra as a generalised arithmetic is what it says in the syllabus. Okay. Now multi-representations. Now Lesch's translation and model we looked at in the last workshop with you, which was all to do with how you approach something like fractions. Because what happens is students come into school with lots of ideas about fractions, but then when you go to work out with fractions with them, those lots of ideas stem down to not very many ideas. And some of the ways to help them out is pictures, spoken symbol, written symbols, real life situations and manipulative models. So not just the one way of expressing something, that there's lots of different ways of getting at the same idea. Okay? So we will discover algebra through the multi-representational approach as well. Now this approach we'll be looking at is story. Okay? What's written there? Okay? What's the written word? Tables. Can we formulate a table from what we're given? Graphs. Is there a suitable graph that we draw? Or maybe there's not a suitable graph that we draw. And then manipulative models that we can use to get the idea across. And then obviously leading on to equations from that. And the whole idea then, the multi-representational approach is, it's not like, again, you know, putting it into procedure of what? I must do this, this and this and this to answer a question. I need to get a table, a graph, an equation and so forth. Sometimes it's what? Appropriate to use a table. More times it's appropriate to use a graph. And sometimes it's totally appropriate to use all 3 or maybe 4 of the ideas together, okay? So representational activities, okay, that's what's mentioned in the syllabus, okay? Now relationships and functions. Through looking at relationships, a student can naturally and be organically introduced to. Now, because remember, if you start off with, functions with students, functions is very specific mathematically. And there's a very specific language that goes with it that our students have to be familiar with, okay? Whereas when you start off with relationships, it's a much looser term, okay? So if you look at, when you're looking at relationships with them, you can get them used to the idea of symbols, you can get them used to the idea of variables, expressions, very simple equations, inputs and outputs of a function, okay, and visual representations of algebra before ever learning procedures. See the way you're talking about inputs and outputs, you're not domains and codomains and ranges and that kind of language yet. You're getting them used to the idea of what actually happens, okay. Now, so emphasize the relationship-based algebra, okay. Now, a functions-based approach to algebra enable learners to have a deep understanding of algebra which allows easy movement between equations, graphs and tables. So this is the key to it, that they can actually fluidly go between one representation to the other. Realise that what? Maybe one representation is letting them down. If I go to the next one, does that move me on another step and so forth and etc. Okay? So that's the idea, that they have a tool bank of things to attack some type of a question. Okay? And the common introductory course is the first place where they'll be introduced to that, and that's the first place where I'm going to introduce it to you today as well. Okay? Now, if you just look at the key outcomes and words there, please, on page 2 of your white book.
Rory, can I just ask you, the common introductory course, every first year in Ireland does the common introductory course.
Exactly.
And it builds on primary school maths.
Exactly. And there's parts of all the syllabus. Now, the common introductory course...
There's parts of the 5 strands.
Yes, but the common introductory course for the first years who would have started last year would only be for 1 and 2. Then the first years who are in first year now, it's 1, 2, 3 and 4. And the first years that are in 6th class now, they will have all 5 strands in it. And it's to get them used to the whole, it's trying to build that bridge from primary into secondary.
And is it felt that then that there would be, that there would be no streaming, that there would be in mixed ability classes?
Exactly. That there would be in mixed ability for this, and that, every student would get the same common introductory course covered with them. And the thing is as well, it does depend on schools. If schools feel that they always have to have a class whose maths is very weak, they might only get that common introductory course done in the whole of first year. But knowing that those students are always going to be doing such a level. But it's not the desired, in most schools that's not the desired outcome for your cohort of first years. Does that make sense?
That's great.
Okay. Now, so your key outcomes and more, just have a look through them there and see, is there any unusual ones in terms of, I suppose, a junior cert currently? Any words that seem a little bit... something that we probably would never have looked at before with our junior certs?
I suppose generalise in words.
Generalise in words, certainly, yeah.
Justify.
Justify. Predict. Any topic there as well that stands out that... Yeah, looking at the slope in a very, very different way. Because look, what does it say about the slope there? The rate of change. Now, that's not a way we would have looked at the slope with our junior certs. It would have been very much what? If you asked the junior cert, exactly, if you asked the junior cert what's the slope now, what would they say back to you? Y2 minus y1 over x2 minus x1. And that's all. And as well, you'll see there that goes well with it then is what? Your rate of change. So what are you getting in? A nice introduction to where their calculus, to build on their calculus for a later stage. Does that make sense? So there's an emphasis there of, look, where are we going with this? Is it just something we're doing for the sake of that's nice? But no, it's not. There's a big, big emphasis for when they go on to look at their calculus. Okay. So the next thing we'll have a look at now is having a go at this. Okay. So we'll try our first problem here. Okay. So we're going to look at our patterns. Okay. So colour blocks. Is there a pattern? I've real life ones here as well. Pattern, folks. What do you notice? Stephen? Stephen? Okay, so you could say what colour whatever one is going to be, could you? Okay, Michael, what do you think?
Probably, yes.
Okay.
From the small sample.
Yeah, small amount of them there, but yet anything that really, what else do we ask about? Can you use the pattern to pick what colour will be at a particular point? So the 20th block.
Black.
Why? Because the even ones are black. Okay, so
Depending on which end you start.
well, let's go with the same as the screen and the same as the one in my hand. Okay, just to keep it correct. Is everybody happy with that?
But it depends whether people decide to concentrate the black one and go left, or concentrate the red one and go right.
Okay, well let's go from mathematics in terms of how we would normally read, which is what? In mathematics, what do we always do? Read from left to right, okay? And the only weird thing is when you'll see with angles later on, you read anti-clockwise, but we read this way. So let's read from left to right, okay? So what have we got? Everyone is, supposing I say the 83rd one.
Red.
Why? Yeah, it's an uneven number. Is everybody happy with that? So very quickly, what have you realised? From a very simple pattern, you're able to realise what certain colours are going to be. Is everybody happy with that? So if we start doing out a table for this, right, to see can we predict anything from it, okay? What have we got? Well, the first one is red, the second one is black, and so forth and etc. So as we said, what did we notice from this? Okay, so now what have I done? What that table just showing? Just showing the black ones. And would everyone agree with the table? The first black is in the second position. The second black is in the fourth position. And is it agreeing with what we said? Why? They're all even numbers. Is everybody happy with that? Okay, so the black, we had said that the black block is always even, and when we went to our table, what happened? That was the case. Okay, now, so what can we say then here? Let's have a look. So here's our block and our position, and we're going to try and come up with some formula. Okay, so if I told you the 10th block, okay, the 10th black block, where would it be, anyone? 20. Why, Stephen?
They're all even numbers.
All even numbers. Okay, perfect. And Joanna, how did you get up to 20, or what did you do to get to 20?
Well, the fifth one was at the 10.
Right, so what did that tell you?
So we were looking for the 10th, so multiplying both of them by 2.
Exactly, you're multiplying both of them by 2. Is everybody happy with that? Okay, and that's exactly what we did. You double the number of the black block, or another way of saying that is what? You multiply it by 2. So how about then the 7th one? Okay, is it Denise beside Joanne? Deirdre, sorry. Deirdre, how about the 7th one? If I say the 7th block.
Position 14.
Position 14, and why are you saying that, Deirdre?
7 by 2.
7 by 2, again. Is everybody happy with that? Okay. Now, Harry, you're going to give you a hard one. So if I told you we were going to call the block N, what did Deirdre do with her one to get it up to 14?
She doubled it.
She doubled it. So what are you going to do with your one?
Going to multiply it by 2.
You're going to multiply it by 2 as well. You're going to double your one as well. So what will we do for that? What will happen? And that will become 2n. Now, it might be a case at this stage, it depends on where your learning is in school, it could be a case of what? You had 7 there times 2 equals 14. So you could have n times 2 equals. Now, there's learning going on there to do what? To get them used to the idea that's the same as 2n. But that depends on where your algebra is at that stage. Does that make sense? Okay, so that's that formula. Now, next thing we're going to have a look at this one. So, Joanne, you did 20. Or Joanna, you did 20, didn't you? What are you going to say now for 20 in this table? Do you think?
20th position or 20th block?
The 20th block.
Multiplied by 4.
Now remember what you did here. Remember you said to me, Joanne, you went from what? 5 to 10, so you multiplied by 2. And then when you went from 10 to 20, you still did what? Multiplied by 2. So use your same strategy again. Look at 5, what did it go to?
Oh, 9. Yeah.
Right, how do you reckon it got to 9? What do you think, John? It's going up in odd, yeah, they're all going up in odds. And how do you... The fifth odd number is going to be 9. Now, isn't that hard? Fifth odd number is going to be 9.
Well, it's 5 minus. It's 5
Double
plus
it,
5
take
minus
away
1.
1.
Exactly. Isn't that easier?
What did
What did you say, Michael?
Double it and then take away 1.
Double it and take away 1. Now, Michael, give that back to Joanna and she'll now answer her question. So Michael said, Joanna, to double it and take away 1. So what will that get you now for your 10?
You're looking for the 10th block, isn't it?
Yeah.
Oh, so 19.
Exactly. Does that make sense? And where is it? It's exactly 1 before the last one I asked you. And doesn't that make sense? Because it's a red. And remember, the reds are always before a black. And then, Deirdre, we asked you for the 7th, wasn't it? Right. And what did you do? You said, well, 7 times 2 got you to?
14.
Right. So now, what are you going to use this time?
The 13.
Exactly. Because it's your 7 times the 2, but I need to come back 1. How do they see that from their physical model? Well, it was very easy to see the black ones, because why? We were very easy to spot that they were even, and that's what you're looking for, something that's easy to spot. But where is a red one always? 1 before a black. And how would you do that in maths? How do you go 1 back? You subtract 1. Is everybody happy with that? Okay. So there's your formula. So what are we going to write for it now? It's very like a black, but what will happen is we need to go back 1. Is everybody happy with that? Now, at a very, very young age, what have they now got the formula for? What are all those numbers? They're even and they're odd. Leaving cert higher level currently would find it very difficult in a sequence or a series to tell you when something is odd and even. Whereas at a very young age, and you can relate back to this, remember we did the blocks, the red and the black? Remember how we worked out our formula for it? And you get them thinking back to, oh yes, I have something logical that I can work towards. Does that make sense? Okay. Now, so what are we doing here? We're trying to get what happens with them. Identify patterns and describe different situations using tables, graphs, words and formula. And the idea there was what? What did you spot straight away? What part of learning did you have very easily? Your evens were so easily for you to spot, but what ones were a little bit more difficult? The odds. Does that make sense? Okay. And then, can you predict from that? And then we moved on to generalising. We didn't really realise whether the formula was justified or not. We haven't looked at that yet. And the next thing we did then was we did come up with a relationship to show that we were correct. Is everybody happy with that? Okay. Now, so I want you to do the next one, and this is on page 3. Okay, so I'm going to get you to have a go at this one yourselves, and you have blocks and all available to you there. Now, an idea that I would suggest, you know, as with the students is get them used to building a pattern. Because everybody, as teachers, we can see that that's the pattern, right? It's very, you know, because if not, what does it just become an exercise in? Building blocks. And the exercise is there some kind of, and if they build like that, it does enhance the idea of being a pattern. Now, don't worry about, the question says, is there a pattern? You know what I mean? You're trying to see what kind of a pattern there is. Don't worry too much about, as teachers I see here just from looking around, what do we tend to try and jump to straight away? An algebraic formula. That's the hard part, folks. That's what we're trying to lead them towards. But you're trying to jump into it straight away, okay? So let yourself through the questions first and let that be kind of maybe the last thing you'll tackle. And remember now, you have strategies available to you to help you with a pattern. Value is not, it's the one that's making the table grow by the same amount every day. Okay. Now, what do you notice about successive outputs? Well, they all increase by how much? 2. Okay. Now, our last one then is Bernie. Now, can you explain to me what's the story with Bernie's?
Cheaper money.
Oh, I never thought of it like that. Okay, well, go on, Deirdre.
So she had a fire and money box was €1.
Perfect. And what about our thrifty Bernie? What's different about Bernie than John or...
She gets a different amount of money.
Yeah, because what's she deciding to do? Obviously, she gets a little bit of extra money at the weekend, pocket money, so what does she say she's going to do? I'm going to save a little bit more at the weekend, and hence we'll see what happens there. Okay, now, so let's look at this one. €4 at the start, then 6, and then 8, then 10, then 15, and then 20. Just looking at those days. Now, I went from Tuesday up to Sunday, just to get in what kind of what idea. What happens during the week? What does she do? Puts in her €2, but at the weekend she's starting to put in 5. Okay. Now, so let's have a look at this thing. Why have I that box crossed out in Bernie's? Let's go back to our table. What about her change? What's the change? Where do you calculate the growth or the change? Where do we calculate it for John or for Mary? It was how much it was increasing by, right? Or changing, exactly. Now, what's the story here though with Bernie? 2, 4, 5, and 6. Why did I need 6 patterns? Because 6 trees are 18. It needed 6 multiples of 3, and obviously it ended with what?
Green.
Yeah. And the 25th one, John?
Yellow.
Yeah. Why?
Because
We were stuck, well, I was stuck in terms of blocks, and so were you, which I did on purpose, which was what? You should have ran out of
Yeah.
blocks, okay? And what was the idea? So we had 6 patterns there, so add another one. How far are we up to now? 21, and another one, we're up as far as 24. Now, your job now, John, is to give me what the 25th one is going to be.
we had it on
Exactly, so I meant it had to be what? Green.
Yeah.
or yellow.
Exactly, it had to be yellow. And at this stage it doesn't matter, because why? You could just go, well, I'm as far as here on the green, that's the 24th, the 25th must be yellow. Okay, the 13th. Well, we've 2 strategies for looking at this. Anyone want to tell us what these are?
12 is a multiple of 3.
12 is a multiple of 3.
So therefore, add 1 because
How many, why do you say the 12 is a multiple of 3?
all the ones that are multiples of 3 are green.
Exactly, and that's the full pattern, isn't
Yes.
it? Okay, so that's it. So you know 12 is the full pattern, then what you need to do, you're starting again, Joanna, so it must be...
Yellow is the one after.
Exactly, you're starting again, so it must be... any other way you might have seen a student that still has to go back and do it this way?
Use black.
Well, they could have just looked at finished out the sequences on any of the ones above.
Or 1, 2, 3, 4, 5, because they have their blocks there. But what they're trying to do is what? The question a second ago, you didn't have blocks to do it. So what they're trying to do is, if you were able to do the previous question without needing blocks, should you really have to go back to the blocks now for this one? Does that make sense? So that's what you're trying to get across to them. Okay. Now, what about the 100?
Again, you're looking at the base pattern. So,
What did you get then? What's
so 99 would be green. The 99 would be green. So what comes after green is always yellow.
Exactly. Is everybody happy with that? The 99 was that many full patterns. Does everybody get that? 99 is what? Going up in multiple of 3s, as close as you're going to get to 100 is 99. Or you could have went what? To 102 and went back 2, but you'll still get the same colour. Is everybody happy with that? The 500. Deirdre?
Yeah, you do the same thing, you identify the nearest multiple.
So how close did you get to it?
498.
498 is a multiple of 3. Yeah.
And then add it on to 2, so we got to black.
Added on 2 more, exactly, so we got as far as black. Is everybody happy with that? Okay. Now, what's a misnomer there the students might do? And even a lot of students do this for the 100. What have they got on the top? 1 to 10. So what do you think some might do for the 100? Well, the 10th one was what colour? Yellow. And what colour was the 100? Yellow. So, you know, they might be getting into their head. But there it's a nice idea. What system is that working on? That they're so ingrained in their heads. The decimal system of counting in hundreds, tens and units. Does that make sense? Okay. So it's a great idea there that to see where it's multiples of 3, so that's not going to hit in as easy. Okay. Now, explain how you found your answers to 8 and 9. Well, I think we've done that as we talked through them there. What did you do? You were trying to get as close as you could to the actual number. Now, what rule? Now, what skill did we look at for getting our rule in the black and reds? Yeah, your table. That's it, Joanne. Your table. So the best thing to do is draw out a table, okay? So just in case you haven't got your table done out. So that was a skill that we learned. It was the easiest to go from the table. So my tables look like that. Is everybody happy with that? Okay. Which table is jumping out at you for easiness? Which one jumped out at us in our red and black example? In our odds and evens, which one jumped out at us? Our evens. Which one here is jumping out at you? Your multiples of 3. Aren't you very familiar with this even from primary school? A student would be 3, 6, 9, 12, 15. So let's come up with a formula for that. So if I told you the 7th one for this Magella, if I had a 7 in here, what would you tell me goes here? 21, because what are you just doing? Multiplying by 3. So now I'm going to put n in Magella. What are you going to then tell me? 3n. Okay. Now, is everybody happy with that? It's 3 times the position of the block. Now let's look at our other ones. We should be very easily able to work from this stage from looking at our pattern. Because if we look, we know now the green ones. Where is a black one always? It's always 1 before it. How do we do that mathematically? 3n minus 1. Okay, 3n minus 1. And then finally for the yellow.
3n minus 2.
3n minus 2. What's the key to making up those that the students will get used to very easily that we forget ourselves? The multiple of 3 was a necessity. And when people go to look at them making up the formula, they often just go with the letter n. Okay, but remember there's a base in the pattern which is what? It's multiples of 3. So there's something there that's getting the ball rolling. So they all have that multiple of 3. Is everybody happy with that? Okay. Same with our odds and evens. What have they all got? A multiple of 2. Is everybody happy with that? Okay. Now, and so there's what it looks like. So you can clearly see there that your patterns working out nicely and your different multiples. So there's loads of discussion that you can go on around there and pick out different numbers and where they actually come from. And look at how much easier our first one is. Purely why? Because of the fact that it's odds and evens. Does that make sense? Okay. Now, the next one we're going to have a look at is the money box problem. So what we're saying is Mary got a money box from her aunt. And at the start, obviously, there was no money in it. But then the growth per day is €2. So we want to investigate the total amount of money in the money box over time. And is the growth of money a pattern? And can we predict how much money will be in the box on the 10th day? Okay, well, could we predict how much money will be in the box on the 10th day?
Just multiply by 10.
Just multiply what by 10?
2.
Multiply the 2 by 10, exactly. Now let's see, does it fit into our patterns in any way? Okay, now let's look at this one then. John and the money box of €3. Is there a pattern to the growth of this money? Now what's different about this one? Well, the idea with John's one was his aunt actually did what? Yeah, so she bought it in the €2 shop out of a fiver and done what? Put the change into the money box, gave it to the child, and then the child does what?
Adding €2.
Exactly. Now, can we use this pattern to predict how much money will be in the box at some time in the future? Do you reckon you could? Okay. How could we investigate if a pattern exists? Now remember, you're dealing with young students. What's our skill that we've learned? Draw out your table. Does that make sense? Now it's harder for us because we're gone straight. What's your head led to straight away? You're mad for some algebra. Doesn't that make sense? But what are we trying to get them used to? You can work these things out and see a pattern, get it into our table. But our heads are ingrained ourselves with algebra. Does that make sense? Okay. Now, so here's the table for John's money box. Okay. So on the first day, okay, literally when it was handed to him, what was in his money box? €3. And then after one day, he put in his money at the same time every single day. What happened? It went up by another 2. Okay. And so on. Okay. And we could follow it right up to what? The 10th day or so forth and etc. Now, is there a pattern, folks?
Yeah.
What is the pattern?
Odd numbers.
Odd numbers, they're all odd numbers. Why are they all odd?
Because you started with 3.
Started with your 3, okay. Anything else then? Anything else you see pattern-wise?
It's the even number plus 3.
It's the even number plus 3. What even number?
The multiple of the day.
Exactly, okay. The multiple of the base. So let's look at our questions now and see where those numbers come in. Where is the start value in euros in that table?
3.
Very obvious, it's the first one. Is everybody happy with that? Now, where is the growth per day as seen in that table? Now, can I remember what was the growth per day? €2. Where is it in that table?
It's increasing.
It's the increase every day. Is it explicitly jumping out at you? No. What about the start value? Start value is the very first one. You can explicitly see it. The growth value is not. It's the one that's making the table grow by the same amount every day. Okay. Now, what do you notice about successive outputs? Well, they all increase by how much? 2. Okay. Now, our last one then is Bernie. Now, can you explain to me what's the story with Bernie's?
Cheaper money.
Oh, I never thought of it like that. Okay, well, go on, Deirdre.
So she had a fire and the money box was €1.
Perfect. And what about our thrifty Bernie? What's different about Bernie than John or...
She gets a different amount of money.
Yeah, because what's she deciding to do? Obviously, she gets a little bit of extra money at the weekend, pocket money, so what does she say she's going to do? I'm going to save a little bit more at the weekend, and hence we'll see what happens there. Okay, now, so let's look at this one. €4 at the start, then 6, and then 8, then 10, then 15, and then 20. Just looking at those days. Now, I went from Tuesday up to Sunday, just to get in what kind of what idea. What happens during the week? What does she do? Puts in her €2, but at the weekend she's starting to put in 5. Okay. Now, so let's have a look at this thing. Why have I that box crossed out in Bernie's? Let's go back to our table. What about her change? What's the change? Where do you calculate the growth or the change? Where do we calculate it for John or for Mary? It was how much it was increasing by, right? Or changing, exactly. Now, what's the story here though with Bernie? 2, 5. What about it? It's not the same the whole way through. Okay, it's not the same the whole way through. Okay, so what's varying each day for each person? Okay, what's varying each day for Mary, John, and Bernie? 2 things. The amount to have in their money box and, well, what change? It varies naturally every day. The day or the time. Is everybody happy with that? What remains constant? The increase. Why have we Bernie crossed out for constant? At the weekend she saves more, so it literally wasn't constant. Mathematically, we don't say something is constant unless it continues right through. Okay. Now, so what I want you to do is, I want you to put these onto your graph. Okay. Now you have a blank one there on page 4, but so you can get drawn on that, please. I'm going to get you to 3 of these. Put time on the horizontal and total money on the vertical. Okay. You should have rulers and pencils there in your pack. Now, just something to, it depends on where they are in their learning. Is it discrete or continuous data?
Discrete.
Yeah. So really, what type of a line should we put between the dots? We should put a dotted line, because why? Because remember, if you think about someone with the money box, what are they doing? If they come in from school every day at 3 o'clock and put money in, what has happened between 3 o'clock on a Monday and 3 o'clock on a Tuesday? Absolutely nothing. Does that make sense? Okay. But it depends on where they are in their learning. Okay. So let's have a look then. Did you notice anything about the graphs? Hopefully now we're all getting to look like this. So there's Mary, John, and Bernie. Anything you notice that's unusual, or which one of the people seem a little bit unusual that the graph tells us very clearly? Bernie. Why is Bernie's graph a little bit different than the others?
Because of the weekend.
There's something happening at the weekend. What did we realise happening? Bernie is getting more money, well, not that she's getting more money, but she's putting more money into her money box at the weekend. What can we say about both John and John and Mary?
They're getting richer at the same rate.
Why?
Because they're getting the same amount every day.
How? Yeah. How do you see that from your graph? What's telling you that from the graph, Harry?
Well, they're parallel, so that's telling us.
Exactly. The two lines are parallel, so they're telling us what? Those two people are growing by the same amount. How come John's always ahead of Bernie? Or sorry, not ahead of Bernie, he's ahead of
Mary.
How come John's always ahead of Mary? Exactly. He had a starting value which put him ahead. Okay. Where do you see those starting values on the graph?
On the y-axis.
Exactly. It's where it cuts the y-axis. So what can we clearly see? Mary had a starting value of 0. John, 3, and Bernie, 4. Now, Bernie was parallel as well for a time, but then what happened? You can clearly see then what happened to the line. Why? What happened to the line? Can anyone tell me how would you describe the shape, or what has happened to it, or anyone? What about the slope, or what?
Change.
The slope changed, or the direction of it changed. In what way?
Steep.
Isn't it steeper? Why? Because now she's putting in more money per day. Is everybody happy with that? She's putting in more money per day. Now, we can see the starting values very clearly in the graph. How about the growths? Where are they? Yeah, but slope. What's this slope? It's very easy for us to say slope.
The constant.
Where is it in the graph? How much the line is changing. Now, so let's look at it for Mary. How much was Mary's changing every day? 2. So let's see, every day Mary was changing by €2. So where does that show us on the graph paper? Well, what have we got? Every day Mary's increased by 2. Every day Mary increased by 2. Every day Mary increased by 2. How about if we decide for John? What do we notice? every day increased by 2. We'll go here for Bernie, every day. Now, how about we go here? Every day increased by 1, 2, 3, 4, 5. Does that make sense? So that's what you're trying to get into their heads about what? The idea of the slope. What is it? It's the rate of change of y's per x's. Okay? So now, if we look at this change, where's the pattern of growth for John's money? Well, +2, +2, and all the way down along as +2. Where did that transpose itself in the graph? Harry told us earlier. What did it mean about John's line? Would we see +2s the whole way down along in Bernie's? No. Okay, so what did those +2s tell us? The fact that they're same the whole way through? You're going to get a straight line. Exactly. Does that make sense? You're definitely going to get a straight line. Okay. Now, what I want you to do is explain in words and numbers how to find the total amount of money in John's box after 15 days. Okay. So explain in words and numbers how to find the total amount of money in John's box after 15 days. Now, what do we know about John? Started out with 3. Isn't that correct? And what did he do? He put €2 in every day. Okay, would everyone be happy with something like that for it? Start was €3, save €2 each day. So John started with what? €3 and saved €2 each day for 15 days. Is everybody happy with that? Now, could we write down then some way in numbers then? Or how would you work out what that figure is? What would we do?
15 multiplied by 2 plus 3.
15. So the amount you're expecting is, what did you say to me, Angela? 15.
15 multiplied by 2 plus 3.
And I'm going to go times 2 plus 3. You happy with that? Perfect. So what are we getting? 33. They're very happy with that. Okay. Everybody happy enough with that? Now, the next thing then, can you see these things from that table? Can you see those in Magella's equation anywhere?
The +2s are all same as multiplying.
Plus,
You keep adding 2 every time.
exactly, and where's that 2 in Mary's or Magella's equation?
Multiplied by 2.
Yeah, here we go. And what else do you notice in Magella's equation? 3. Where is it? Here. Okay, now let's just look then, like we did with our other patterns. I want you now to generalize. Now, what's the only difference between this and the last one? It said words and numbers in the last one. Now we have words and symbols. So see, can we convert our red and our green one using symbols? Now, what do we mean by symbols? Well, they're just letters that stand for something. So give me a symbol that you might use for amount. A. What are we hell-bent on? Magella is hell-bent on it.
Oh, I know, my X.
Yes, exactly. Is a student going to say X to you? Not in first year, okay? Not unless they're up doing Maths Olympiad up in DCU when they're in 6th class. But at the end of the day, A is for amount, so doesn't that make logical sense? And then they can use what? Maybe N for the number of days or whatever the case may be. So I'll just let you come up with some formula that you think is correct, okay? Using your symbols. Okay, John, just purely because your name is on the board, can you read this sentence out for me and tell me what numbers I need to get rid of, or maybe what numbers I need to keep?
Just started with €3.
So you're keeping this?
Okay.
Yeah. Okay.
Oh, sorry.
So I'm just after saying you said €3, so we're keeping that one. You're happy with that figure? Perfect. And?
I said €2.
Right, so you want that one as well? Perfect. Now, do you want to keep the 15?
It doesn't really matter. For N, you could use N for the days.
It doesn't really matter. Okay. Right, so for 20 days then, you're telling me that my answer is 33. You said it is. Because you said that 15 doesn't matter.
Yeah. Okay.
Does that 15 matter?
It does in this case.
Exactly, because what does that 15 do?
It gives you, it tells you
So suppose
what you're
you
going to end up with.
Yeah, let's move it to 16 days. What's the story, John?
Okay, you increase it by 2.
Exactly, because you have 16 by, which is your 32, plus 3 is 35. Is everybody happy with that? So that 15 is important. So what are we going? What did you want to call it then?
Yeah, call it N.
Call it N. Okay, so now we've called that N. Now, John, can you rewrite?
Okay. You can have 2N plus 3.
Okay, so instead of, let's go here. What will I say for amount?
A is equal to 2N.
Okay, well, N here times 2. We just write it like just to keep it together. And then?
Plus 3.
And then equals what?
Equals, yes, equals A.
Exactly. Why? Because we don't actually know. A very different situation than Magellan's, because why? Once 15 was there, we knew that that's what gave us 33. When we asked John to do 16, what did he say? That was 35. But now when it's N, we don't know what the answer is going to be. It's for all the numbers. But now we'll just tidy it up and we have what? A is equal to 2 times the number of the day plus 3. And are we happy that that'll work? Well, let's do it for our 15. 2 times our 15, 30, plus our 3 gives us our 33. So you have a nice introduction to what? Letters and how they come into equations and so forth and etc. Now, another thing about it. What did you notice? What was the only thing that changed there between Magellan and John's? Yeah, the number of days. They both stuck with the 3 and they both stuck with the 2. Okay, is everybody happy with that? Okay. Now, what is the general formula for Mary then?
It's just 2N. A equals 2N.
Well, let's have a look. What do we call this? We know that this is the starting, sorry, not the starting, this is the, let me go to the next slide because we're a bit squashed there. So what did we have? We had A equals 2N plus 3. So what was the 3?
Your starting amount.
Starting amount. Okay, what about this?
Is your days.
No, your 2.
Oh, sorry, then. What's your increase?
Your growth. Is everybody happy with that? And then your N was your number of days. Now let's see then, where were these on the graph? Where was the starting amount on the graph? Where did you see it? Our y-intercept. And then where did you see this part? Well, it depends on where the learning is. It could be the slope if you've that covered. or it could be just something like that for the time being if you're only at that stage, over 1 and how much it went up. Is everybody happy with that? Okay, so they have that much learned. Now, so we're trying to go then for Mary's formula from John's formula. What does it have in it? We need a growth and we need a starting amount. So what's it going to be for Mary? Well, obviously we'll just say A for amount. Now, what's Mary's growth?
2n plus 0, so it's 2n.
2n, exactly, because why? The growth is 2 plus 0. Give me 2 places where you'll get that 0. 2 places you can find that 0.
The x and y.
Your table, and what's your other position? From your graph, it'll be the y-intercept, okay? And then how do we usually write this? A equals 2n. Now, will I be asking you to write a formula for Bernie?
No, because the number of days.
No, I won't be. Exactly, because why? It's not linear. Remember what we said? John told us earlier, because we had that 2 the whole time, we were getting a straight line. And because of those straight lines, these nice properties come out. Bernie didn't have that property because she had 2 changes. So it's not linear. So we're not going to go down the road of trying to get her equation. Okay? Now, then to look at them like this then, can you read John's starting amount and can you read Mary's rate of change? Okay, so what's John's starting amount?
3.
And what's Mary's rate of change?
2.
And the idea there is what? To get them used to the idea that it doesn't matter what way you write it. Is everybody happy with that? That it doesn't matter what way you write it. And as well, to remember when they're looking at it, well, is it the 3 that's by the D or is it the 2 that's by the D? Now, does the D make any difference? John used N, I used D. It makes no difference. Now, so which thing makes it grow? Every day of the week, it grew by the 2. What about the 3? You only got that once at the start, so it wouldn't make sense to be multiplying that every day. Does that make sense? So you can start talking about things like that with them as well. What are we leading on to, folks? What did John say we described? Beginning with L. Linear functions or linear graphs even. What form did they come in? So what have they naturally discovered themselves? The slope is what's in front of your x, and then it has a constant if it is a starting value or a y-intercept. Does that make sense? So the logic is there from them from a completely different emphasis. Okay?